Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a course of lectures in the section on interference of light, and in this lecture, that is the lecture number 15, the contents will be as follows: change of phase due to reflection, colors of thin films, conditions for constructive and destructive interferences, interference in thin films, conditions for bright and dark bands. Essentially, what we are trying to do is to give the theory of the phenomenon of interference, which is to be applied to the case of air wedge. What do you mean by air wedge? We will see in a few minutes time, or in other words, the colors of thin films which we have been talking about, in the sense that when you walk in the road, as I told you, you see when water is there, on the surface of water, if you have got some petrol or oil, it acquires some color, and see a colored surface, and this is called colors of thin films, because the film thickness or the layer that is formed on water due to petrol or some oil, that layer is of minute thickness, and that forms a film. Because of that film, it acquires color, and so as I will be showing you again the colors that you see, this phenomenon is due to interference. Before I go further, I would like to remind you the two important things. I will be talking many times about path difference. You should understand what is meant by path difference, and again the first point, change of phase due to reflection. As I told you in the last lecture, when light ray is incident from air to glass, you have got a glass medium, and a light ray is incident here, this is air. So, light ray is incident on the surface of the glass. When it is reflected, it will undergo a phase change. How much is the phase change? It is pi or lambda by 2. Okay. So, what is meant by path difference? Another important point that want to emphasize, because the fact I will be calculating the path difference in the problem which is going to be discussed now. So, I told you some time back about path difference. Let me now, for the sake of completeness, let me tell you once again what is meant by path difference. Supposing you got a slit S1 here and slit S2, we have been discussing about Young's double slit experiment. This is source is capital S, and the light coming from this source is distributed. You have got S1 will act as a source, S2 also will act as a source. These two sources will be called the coherent sources, because they are coming from the same parent source. From S, from source S, light is passing through S1 and passing through S2. These two slits are separated by a distance d. That is not very important, but the point is when the light beam goes and hits at the screen here, the light beam that is coming from S2 is going and hitting at a point P. At this point P, the light waves interfere with each other, that is the light coming from this, you have form of wave, you got the crust and then trough, crust and trough and so on. So, it goes here at a point P, and similarly the light coming from S2, the light wave, you got a crust and the trough and then the crust and then trough and so on. Okay. Now, what is meant by path difference? I told you some time back, the extra distance, the additional distance travelled by one light beam compared to the other light beam. Let me now ask you whether S2p, this distance is larger or S1p is larger. Obviously, S2p is larger, right. S2p is larger compared to S1p by how much? You draw a line perpendicular to, this is the delta. What is delta? Delta is the additional distance, this is R2. R2 is obviously larger than R1. This R2 minus R1 is called the path difference. Now, let me ask you the question, supposing at S1 you got a crust and S2 also you got a crust, and from S2 to this point you supposing you got a full wave, that means at this point also you got a crust and here also you got a crust, then what will happen to the resultant at a point P? Let me again tell you, at S1 you got a crust, at this point also you got a crust, right. Okay. You got a crust here, and so because lambda being the same, you got a crust here, then the two crusts will come and meet at a point P. When a crust meets a crust, what will happen? There will be a constructive interference. So, at this point P, there will be a constructive interference provided you get a crust here and a crust here. This distance delta consists of one full wave, that means you have a crust here and then a trough here and then goes like this, right. You have got a one full wave, you can imagine the crust and then trough and so on. So, anyway, if this delta consists of one full wave, then you have a crust here and a crust here, then at the point P there will be constructive interference, or in other words what I would like to tell you is, if the path difference is lambda, the delta is lambda, one full wave, right. I told you that I have a full wave here, right. You have got a full wave, you can imagine a full wave here. On the other hand, you have got only half lambda here, that means when you have got a trough is coming here and a crust is coming here and a trough is coming here, then the crust and trough will meet here, right. When a crust and trough meet, what will happen to the resultant? The resultant will be equal to 0 at a point P, will have that is a condition for what? Destructive interference. So, at a point P, the intensity will become equal to 0. That is a case for understanding constructive destructive interference. Okay. At a point P, there will be destructive interference if your delta is lambda by 2. Let me repeat again, if delta is lambda, that means if the path difference between the two light beams is lambda or 2 lambda or 3 lambda, as I told you in the previous lectures, if the path difference is integral multiple of lambda, that is the condition for constructive interference, because a crust and a crust coming from the two sources will meet, or a trough and trough will meet, giving rise to constructive interference. On the other hand, if the path difference is lambda by 2 or 3 lambda by 2, lambda by 2 means half wave, 3 lambda by 2 means 1.5 waves, 5 lambda by 2 means 2.5 waves. So, if that is the case, the crust and trough will meet leading to destructive interference at a point P. Therefore, the path difference is important. What is the path difference? It is extra distance, the additional distance travelled by one light ray compared to other light ray, or one light beam compared to the other light beam. The excess path travelled by one of the light rays is called the path difference, right. Okay. That path difference I will be calculating in the case of air wedge. I am continuing with colors of thin films. As I told you, if you got nice soap bubbles, you got a soap bubble, So, this is the thickness of the bubble, I mean the thickness of the film, right. You got a bubble, you will be having air here, you will be having the atmospheric air, you got inside there will be nothing, you got a soap bubble, you make soap bubbles, right. So, you have in the hand soap bubble. So, the bubble acquires coloration because of the phenomenon of interference. So, we are talking about the colors acquired by thin film. What is a thin film? This is the thickness of this layer that you got a film here, right. And so, then this is a thin film, right, of a few nanometer thickness, right. Or in other words, in a case of oil spill over water, when you walk along the road, you get this is a film developed here, and you get colors, a pattern of colored light formed by interference between the white light being reflected from the surface of a thin film of diesel fuel on the surface of water. On the surface of water, you got some petrol or diesel, if it is falling on that, will be a thin layer formed, and that will give rise to coloration. Most of you would have seen it when you would have walked on the road, but you would not have cared to understand what is what, but that is due to the so called interference phenomenon. Let me now once again explain what is meant by path difference. Now, you got an incident light falling on this surface, this is air here, and this is the film I am talking about, right. What do you understand by this is the film, right. This film is of this much thickness, right, a very small film, right. Thickness will be very minute, will be a few nanometer to 1 micron. Okay. This is a thin film, it is magnified, this is a film, the thickness of the film is d, light is incident on the surface of the top surface of the film, reflected in this direction. Part of the light will be transmitted and will undergo refraction and be incident on the bottom surface of the film, and again it will be reflected and goes in this direction. Now, what is the extra distance travelled by this light beam? You got one reflected light, another reflected light beam. Now, one light beam is going straight along AD, whereas the other beam travels through a distance AB, then BC, and then it travels along this direction. This extra distance travelled by this light beam, the second light ray that is travelling from the point C, whereas the light ray passing from A goes straight. So, you have to calculate what is called the path difference, that we will be calculating. Then depending upon the condition, if the path difference is integral multiple of lambda, that will be constructive interference. If it is integral multiple of lambda by 2, then the two light beams will interfere destructively, right. If they interfere constructively, then there will be constructive interference, giving rise to a bright band. So, the degree of constructive or destructive interference between the two light waves is dependent upon the difference in their phase, the phase difference or the path difference. This difference is dependent upon the thickness of the thin film layer, the refractive index of the film, and the angle of incidence of the original wave on the film. Additionally, you should know by now, as I told you, when light ray is incident on a denser medium, the light ray coming from a rarer medium, it is incident on a denser medium, it will undergo a phase change of 180 degrees. That should be remembered, that should be kept in mind when we proceed further. Additionally, a phase shift of 180 degree or radiance may be introduced upon reflection at a boundary, depending on the refractive indices of the materials on either side of the boundary. This is what I told you just now. So, a thin film is a layer of material with thickness in the sub nanometer to micron range. This is a thin film, right. This is a thin film. As light strikes the surface of a film, it is either transmitted or reflected at the upper surface. Partly it will be reflected and partly it will be transmitted. This is what we saw earlier also, repeating the same thing. Okay, the light ray is incident, partly reflected, partly transmitted. That transmitted beam again will be undergoing a reflection, and then it will be coming in this direction. Now, we are concentrating on the two beams R and V, that is QR, the light ray here, and UV, the light ray coming here. These two will be interfering with each other that will lead to either constructive or destructive interference. And what is the path difference? This light ray P q at the point q it is reflected, it is going in this direction, whereas this light ray, that is a light ray 2, it goes through a extra distance q s, reflected again, it comes through again the same distance q s will be obviously equal to S u, same distance, and then comes here. Okay. This is the extra path travelled by the second light ray. This is the first light ray, this is the second light ray, these two will interfere, right. The second light ray is travelling through an extra distance q s plus S u. Obviously, q s and S u will be the same, right. It is a reflection, it is a light beam incident and they are reflected. So, the q s and S u will be the same, the angles of refraction are the same. So, the lengths of q s and S u will be same, and remember this distance travel is not in air, but in a medium which has got a refractive index mu, that should also be remembered, that will come in the calculation. Light that is transmitted reaches the bottom surface and may once again be transmitted or reflected, that will partially there will be transmission. Now, we are not concerned about this transmitted ray, but we are concerned about the reflected ray and how this light ray q r and u v, they will give rise to either constructive or destructive interference, that depends upon the path difference between the two light rays. So, consider a film of uniform thickness T, right, the thickness T here. So, the thickness of the film is T, the refractive in the film is mu. Let us assume that the light rays travelling in the air are nearly normal to the two surfaces of the film. The light reflected from the upper and lower surface will be interfering, right. As I told you, light reflected by the upper surface and light reflected by the lower surface, these two light rays q r and S q v or u v, these two light rays will be interfering. That depends upon whether you are going to get a constructive interference between the two light waves or destructive interference will depend upon the path difference. We have seen the condition, the path difference is integral multiple of lambda, that will lead to constructive interference. If it is integral multiple of lambda by 2, that is the condition for destructive interference. So, let us look at the triangle SMU. Our aim is to calculate the path difference. So, what is your SU? The SU is the distance, right, this distance, and that will be equal to QS, obviously QS and SU should be equal, and SU will be T by cos r, or if you look at the triangle, what is cos r? Cos r is the angle r, cos r will be what? SM by SU, right, SM by SU. What is SM? SM is the thickness of the film, right. So, SM will be the thickness of the film will come here T. So, cos r will be T by SU, okay, T by SU. So, your cos r will be T by SU or SU will be T by cos r. So, essentially SU now will be equal to T by cos r. Similarly, we have to know QS also. Why should you know QS? Because the light ray coming from here, one of the light rays is reflected in this direction, right. Then the other light ray goes through a distance QS plus SU and comes here. So, from this point you draw a perpendicular, right, from you draw a perpendicular to this light ray. So, by the time the first light ray comes to N, then you have the light ray here coming from QS to SU and then it comes here, then the path difference will be what? QS plus SU multiplied by the refractive index minus Qn, right, because it is extra path, right, extra path is what? QS plus SU, but it is taking place in a medium of refractive index mu. So, you got QS plus SU multiplied by mu minus Qn, right. This is the path difference obviously will be minus Qn will be there. Okay. So, your the phase shift occurs if the refractive index of the medium and the light is travelling through is less than the refractive index of the material as is striking. That is what I told you. The two light rays, that is a phase shift will occur upon reflection, that is pi. The pattern of light that results from this interference can appear either bright or dark, depending upon whether it is going to satisfy the the constructive interference or destructive interference. Consider a transparent film of thickness T and refractive index mu, and A B and C D are the top and the bottom surfaces. So, you have here the light ray P q is incident on this surface, okay. Then all these things are known. So, you got q s here, s u here. Let us now go to the mathematics. So, your the two light rays I was telling are P q s u v, this is a P q s, you know P q s b, this is the light ray P q s b here. The other light ray is P q r, right. Okay, you got P q r, the ray 1, the other the one is the P q s u v that goes inside and comes out the ray 2. Ray 2 has travelled a greater distance compared to ray 1, because it goes through the film, at the bottom of the film only it gets reflected. So, how much is the path difference? You have to know the path difference between the two rays can be determined by drawing a perpendicular line that I told you. You draw a perpendicular from u to this light ray. So, this is the perpendicular drawn. So, this light ray comes here, and you know this and this are the same points. I mean, in the sense that the perpendicular drawn here, thereafter there will be no path difference from n r to u v, this distance will be the same, right. So, this light ray comes through q n, a distance travelled through q n, whereas this light ray goes through q s plus s u multiplied by mu, whereas this one only goes through a distance q n. Then thereafter there will be no path difference. Okay. So, the additional path travelled by this light ray will be q s plus s u multiplied by mu, because it is travelling through a medium of refractive index mu. So, this will be q n. So, the path difference will be mu times q s plus s u, okay, mu times q s plus s u is the extra distance travelled by this beam minus q n, right. So, your the path difference will be mu multiplied by q s plus s u minus q n. Now, q s and s u will be one and the same. As I told you, q s and s u will be one and the same, already shown q s to be equal to T by cos r, or s u, right, s u is T by cos r, this will also be T by cos r. Okay. So, T by cos r plus T by cos r, this getting repeated, T by cos r is also again T by cos r. So, that extra distance travel is T by cos r plus T by cos r multiplied by mu. Okay. This is the q n will be here. So, the path difference will be written as now mu times q s plus s u minus q n, but your q s and s u are both equal to T by cos r. So, this will be T by cos r plus T by cos r. So, let me now write x to be equal to T by cos r plus T by cos r. Okay. This will be 2 T by cos r. Okay. Then from the triangle q s sum, sin r will be equal to q m by q s. Therefore, q m will be equal to q s into sin r. Therefore, your q u will be 2 q m, that will be equal to 2 q s sin r, that will be equal to 2 t by cos r into sin r. So, you consider the triangle q u n, from that you can find sin I to be equal to q n by q u, and q n will be obviously q times q u times sin I. From the above equations you will be getting q n to be equal to 2 t sin I into sin r by cos r. So, Snell's law shows the refractive index mu will be sin I by sin r, or sin I will be mu times sin r. So, from the above equations you will be getting q n to be 2 t times sin I into sin r by cos r. So, from the above equations it can be shown that the path difference between the two light beams to be equal to 2 mu t cos r. Let me now summarize the points which we have understood from this lecture. 1. The colors of thin films which appear on the surface of oil and water or soap bubble or due to the phenomenon of interference. Light reflected by thin film causes bright and dark fringes depending upon the conditions satisfied by constructive or destructive interference. Here are the questions: what is meant by path difference? When a light wave undergoes reflection when it passes from a rarer medium to a denser medium, how much phase difference it will undergo? Then the last question is, what do you understand from the words colors of thin films? With this we come to the end of this lecture. The mathematical expression which is to be derived for showing the bright and dark bands will be taken up in the lecture to come. Thank you.